Today's video has two main objectives. The first is to recognize how additive colors affect the color of light, and the second is to recognize how pigments affect the color of reflected light. White light is not a single color, but simply it's made up of a mixture of the 7 colors of the rainbow. We can easily demonstrate this fact by splitting white light with a prism. The beam of light enters the prism from the left, then as it refracts through the prism, all of the different wavelengths get bent. This is actually how you get a rainbow. The sunlight gets split up by the raindrops that are in the air. The colors of the rainbow are just what you would expect them to be based on your prior knowledge: red, orange, yellow, green, blue, and violet. That white light can be split up, but we can also add those colors back together again. So white light can be split up to make separate colors, and these colors can be added together again. The primary colors of light are red, blue, and green. All it takes is those 3 primary colors to make any other color that's possible. Here's our color wheel for the additive mixing of light. Again, red, blue, and green are our primary colors. When we mix red and blue together, we get magenta. Mixing blue and green together makes cyan. Mixing red and green together makes yellow. What you're looking at is that additive color wheel. All 3 of these primary colors get added together to form white light. Now would be a good time to hit the pause button and copy this color wheel down. When you watch TV, you're actually only watching those 3 primary colors being added together. Your color monitor can only emit red, green, and blue light. You get all of the other colors that you see by selectively turning off either the red, the green, or the blue pixels. So in this example, we're kind of focusing in on the yellow in the screen, and notice it only takes red and green light to make yellow. Complementary colors are any 2 colors that when added together produce white light. The pairs of complementary colors, blue's complement is yellow. That's because blue plus red plus green gives us white. Green's complement is magenta. Again, green plus the blue plus the red gives you white. Red's complement is cyan. The primary colors are red, blue, and green, and then we have secondary colors called yellow, magenta, and cyan. Adding different amounts of all of these different colors gives us an infinite possibilities of shades. Tertiary colors, you can see on the color wheel, you mix a primary and a secondary shade together. So for example, if we took red, our primary color, mixed it with yellow, our secondary color, that's how we get orange, which is considered a tertiary color. You don't need to know what colors the tertiaries would be, just understand the definition, that it's a primary mixed with a secondary. When we mix different lights, again, we get different shades and different colors overlapping. Take a look at these 2 pictures. Okay, the picture on the left is showing hands that are actually in a red, a green, and a blue spotlight. And what he's able to do is cast shadows on his fingers in lots of different shades or lots of different colors. If you notice this image on the left, there's your blue, there's your green, there's your red light. Notice how the green and the red make yellow, the green and the blue make cyan, and then here we get our magenta with the blue and the red kind of mixing together. One cool thing that happens with colored lights is the creation of different colored shadows. If you just think about a typical shadow that you might make, you've got your point source of light, you've got the object blocking it, and then this entire part of the screen basically gets blacked out because no light is able to hit that part of the screen. When we have more than one light source, if you kind of follow these ray tracings, look at light source 1, I trace it to the edge of the card in both directions. Light source 1 cannot hit this part of the screen. Light source 2 gets blocked here and gets blocked here between A and C. Both light is blocked in this stretch of the screen. That's considered an umbra. That would be what we call a total shadow. But here between A and B, we're getting a partial shadow. Light source 2 is blocked, so light source 1 diffracts and fills in that space. Over on this side, light source 1 is blocked, and so light source 2 fills in all that space. Let's take a look at an example. Okay, What this applet is showing is the light source, the object, and the shadow pattern that would be created on the screen. Okay, I'm going to add in those light rays to hopefully kind of make sense with what's going on the screen. So our light source gets blocked between this position and this position on our screen, so we get no light. We would get a total shadow or a black shadow. On this part of the screen, the red light fills in that open space, so the screen would be colored. If I add in a second light source, hopefully you noticed a couple things. All of a sudden I've got some yellow, I've got some red, I've got some green, and I've got some more yellow showing up. Let's take a look at what's happening. Okay, the red light is blocked from this position all the way down to this position. What that leaves then is this green light kind of filling in that open space. Up here, the green light is being blocked. The red light fills in this open space. The very top and the very bottom of the screen, absolutely no light is being blocked, so what we're getting is red and green light mixed together. If I add in a third light source, then I create even more shadows. Okay. Hit pause on the recording and see if you can figure out and explain what's going on with all of the different colors. Take a look at what's being blocked, what light is left to add together, and then the resulting colors that you get from that. The reason that we're able to see color in the first place is because of the light that it's able to reflect. A red book, for example, is reflecting only red light. We illuminate it with all the colors of the rainbow. Every color but that red is being absorbed, and we see only what is capable of being reflected. A pair of purple pants, everything would be absorbed except for that purple light. So we see colors because of what is being reflected. Something that's white would reflect all of the colors of the rainbow. If we look at a colored object in colored light, we see something different. Okay, consider the following outfit. I've got a red shirt and I've got blue shorts. Our white light, our three primary colors of red, green, and blue, are shine on our outfit. The red shirt reflects only red light. That's why it looks red. The blue shorts look blue because it's only capable of reflecting blue. If I put this outfit in different colors of light, it's going to look different. So take, for example, just shining red light on it. The red shirt is capable of reflecting that red light. The blue shorts are not. That red shirt then would look red, but the shorts would look black. The shorts are not capable of reflecting any of the light from the source, so we would see this as no color. What if I shine blue light on this outfit? Hit pause and take a guess. Okay, did you guess that the blue shorts would still look blue because they're capable of reflecting the blue light? The red shirt, on the other hand, would look black. It's not capable of reflecting that blue light, so all that's happening is that it's absorbed. Let's try some more examples. Okay, if we take a red sock and we shine red light on it, the color is going to look red. Red socks are capable of reflecting red light, but they would absorb everything else. Under blue light, those red socks are going to look black. We're not giving it any color that it's able to reflect. Under green light, they would also look black. Again, red cannot reflect green. If we can't reflect any colors, it's going to appear black. Okay, our blue teddy bear under red light is going to look black. Again, I'm not giving it any colors that it's able to reflect. Under blue light, the blue teddy bear would look blue. Under green light, it would look black. Okay, let's think about the green camel. Under red light, it would look black. We're not giving it any light that it can reflect. Under blue light, it would also look black. But under green light, it would look normal. It would look green. Okay, let's up the ante a little bit and let's look at an object that looks magenta. So it's already a secondary color. Think about magenta. It's made up of both red and blue light. So if I shine a red light on it, that book is going to look red. It's capable of reflecting red light. If I shine blue light on our book, it's going to look blue. Because it was magenta under white light, it's capable of reflecting that color. Under green light, I'm not supplying any of the colors it's able to reflect, so it's going to look black. Let's switch gears a little bit and look at how we're able to subtract or take out colors of light. And let's focus on filters first. The subtractive process takes out colors from white light and tells us what we're able to see. Okay, a yellow filter allows only yellow light to go through, but blocks everything else. Typically what happens is the two colors of light on either side of it, a little bit of that goes through as well. So we're going to see mostly yellow. If I have a blue filter, that means the blue is allowed to go through, but everything else gets subtracted or taken out. If I have a blue filter first, blue light is allowed to go through. Then a red filter would only allow red to go through, but I don't have any red, so we're going to get black. Pigments are another way to subtract or take out colors from light. So pigments subtract or absorb light. Notice the subtractive color wheel on the left. This particular pigment is absorbing green because it's made up of red and blue light. A cyan pigment is going to absorb red because it's made up of blue and green light. Yellow absorbs blue because it's able to reflect red and green light. If I mix all three of these together, that's how you get black, or the absence of light. When you print something off, that's actually what you're using, is the subtractive color process. If we look at this picture and keep zooming in up to 800%, hopefully you can see that what you've got is magenta, you've got cyan, and you've got yellow pigments. When those pigments overlap, that's how you get your reds, your greens, your blues, and even your blacks. Let's try a few examples. Okay, what color or what inks would we use to make the bird below? Okay, here's our subtractive color wheel for reference up in the corner. Okay, if I wanted to make the red part of my bird, I would need to mix magenta ink so that the magenta ink so the green gets absorbed, and I need to add yellow ink so the blue gets absorbed. If I do the yellow feathers, it only takes yellow ink so that blue gets absorbed, red and green get reflected. With the green tail, it would take yellow to absorb the blue and cyan to absorb the red. That's a C, sorry. If I want to make the blue part of the bird, I need magenta ink to absorb the green, and I need cyan ink to absorb the red. If I do the top part of his chest, that's cyan, so all I need is cyan to absorb the red. Blue and green are what's going to be reflected. Let's try one more. Okay, how about this person? Okay, if I want his red shoes, I need to use magenta ink to absorb the green, and I need yellow ink to absorb the blue. If I want to do his cyan socks, all I need is cyan ink, because the red would get absorbed, blue and green would be reflected. If I do his blue pants, I need to use magenta ink and cyan ink. See if you can supply your own explanation for that. To do his yellow shirt, all I need is yellow ink. And then let's assume his skin is a version of magenta. So all I would need is magenta ink to produce the skin. Okay, please go back and watch any part of this video that you need help with. Don't forget physicsclassroom.com is another resource that you can use, and come with your questions tomorrow.